So the skewed thing, you kind of have to draw it out. I didn't spend a lot of time on it. I don't think any time in class, because it's one of those things that doesn't really tell us too much. So if you were on page 94 of your book, in a perfect world, we'll have a distribution. It'll be two things. One, it'll be symmetric. Symmetric means you can fold it over on itself and it's the same. Right? Usually when we talk about symmetry, we talk about it in terms of shapes or letters. So just so you know, the letter V is symmetrical. Right? You can fold V over. You can stop it. You can fold the letter V over onto itself. Okay? Symmetry is something that we observe a lot in nature. I hate to break this to you, but ladies, it's the reason why you wear makeup, is to create more symmetry in your faces, which is what is attractive to other people, is symmetry. So in a good, perfect world, we would have symmetry in a distribution. And if we have symmetry, then the median, which is the middle number, the mode, the most frequent number, and the mean would all be the exact same. Okay. So here we have a distribution that is symmetrical. And the book also talks about how many modes there are. How many modes are there in this distribution? How many peaks or bumps are there? One, all right? So this is both unimodal and symmetric. So is this distribution skewed in any way? No. This is the ideal. This is the one that we want. There is no skewness here. What happens is that you can have a skewed distribution where, I gotta really practice this one. Where our curves are not symmetrical. So if we were to try to fold this in half, hopefully, and I know my drawing skills aren't great, but you can tell that this tail here, this side, and this tail on this side are longer. So if we folded them over at the median, it wouldn't be a perfect fit. These are known as skewed distributions. And this happens when you have, let's say, the mode. We know it's the mode because it's the highest point, which means there's the most frequency at that number. Be on the left of the median and the mean, right? So if you look on page 94 of the textbook, it shows you the examples of how the distributions get skewed based upon the position of the mean, the median, and the mode. Okay. Again, we can observe in real data how they fit this curve, and we can understand that perhaps there's the presence of outliers. So thinking back to why it is we would want to observe data, right? This is a distribution that's skewed to the left, which means that there are outliers on the right. If this is shoe size, and the average shoe size is 9, we got to pretty much start at 0 because you can't have negative feet. I guess I could go backwards, but All right. Who is out here? Shaq. Right, with his size 23 feet. So there are a group of people in the United States that have abnormally large feet. Most of them are playing professional basketball or organized basketball in some form or fashion, or sports. Or they could just be really husky. Okay? So the presence of these outliers, like Shaq and other people with ridiculously large feet, not to just throw the basketball players under the bus, but competitive swimmers. We had the Olympics this summer. Believe it or not, Aaron's making a face. Competitive swimmers have a body type. They're usually over 6 feet tall. They have a leanness to them, and they also have freakishly large feet. Why? Flippers. I am not making that up. Okay. Also hand size, because again, you think of the hands as paddles. Okay. They're outliers. They skew the distribution of all the people in the world. Okay. So that's what that question was asking about. If you have a set of data where the mean, the median, the mode aren't very close, chances are what's happening is you have some outliers that are skewing the shape of the distribution to the left or the right.
So which one's negative and which one's positive?
It doesn't matter. Doesn't matter. Don't worry about it. I'm not worried about that.
So it's freebie.
Yeah, it's a freebie. Everybody had a question about it. And I didn't spend any time of it in class, which showed you how important I thought it was. Yes, because I'm evil, and I like to do that. Clearly, evil. Yeah. All right. So that's what it is with skewness. Yes, it's nice to sort of know because you'll hear this. Oh, well, this is skewed because of, and that's something you would hear in conversation. We were talking about people trying to criticize your data. But quite frankly, if you have a large enough data set, this won't matter. When this matters is when you have a really small data set. Okay. Let's say this is a stats class and we're creating a data set of foot size, and this whole first row is the men's basketball team. We would see that skewed, right? The fact that 1/3 of the class has a shoe size in the 20s. We would see that in our data. But most of us are normal people. I don't see any gigantic feet among us. What do you got there, Nick? 13, that's not that bad. Anybody beat 13? Ben? No? 12? Nobody? Tom? 12? Yeah, nobody's a freak with their feet in here. We're good. But when we do thousands of people, 2,000 respondents, yeah, you'll find some guy that has a size 18 shoe size. But it's okay, because there's a couple thousand people that'll drown him out. And then there'll be that person with the freakishly small shoe size that like has a 5. They'll cancel each other out. And that's why I'm not worried about it, because when you guys are going to be looking at data, something like the GSS or the NES, you're going to be having data sets with thousands of people in it. And we won't have to worry about this so much. Make sense? Okay. Any other questions? Which ones gave you fits? All right, I'm going to do one, because there was one that a couple of people came to talk to me about. And it had to do with the frequency distribution tables. And it asked you to compute the mean, where x bar equals the sum of fx divided by n. Anybody remember looking at this one twice, trying to figure it out? Okay. It might have been confusing for a couple of reasons. One, the textbook didn't call this X. It called it score. And so some people are like, well, what's the X? X is our variable of interest. Okay? It's what it is that we're measuring. It is our data. Okay. So the score was actually the X. Now, what people got confused about is where it said FX. Well, which one is FX? I don't even have an X on the table. Which one is the FX? Is it the one that's not labeled, the little percentage? No. FX is a mathematical expression. It's asking you to take F and multiply it by X. Maybe if they had like a little dot in there or something to denote that FX isn't a thing. It's an expression, F times X. So what it asked you to do was compute FX. Well, bucket on the floor. We're going to simplify this. We know we have to multiply these two numbers together. And then we have to take the sum of it. And then we have to do 43 divided by n. Where does n come from? Well, n is the total number of observations. N is also the sum of f. 5 plus 3 plus 6 plus 2, 16. Okay. So you had to sort of understand how the frequency table worked in order to get the data out of it. If I wanted to bucket on the floor this, how could I do that? How could I take this frequency table and turn it into something else so that I could see what the data are? What would I need to do? Okay, so where do I start? Okay. Right? Oh, yep, thank you. Did 4, 4. So this is the same thing as that, which in question number 8 you did already in question number 1 and 2, and right? So it's just taking what is unfamiliar and figuring out what it is that is familiar to you. Bucket on the floor. All right. Any more questions about the homework? Those were the ones. Danny?
So, n then isn't like, you know, when we do mean and we count how many there are that we're dividing into the whole sum.
Mm-hmm.
So n wasn't that then for the frequency distribution table?
Okay. N is the number of observations, which is also n equals the sum of each value that is observed, or how frequent a thing is observed. So when you look back at that table, this number here, f, is the frequency in which we saw each individual number. So we saw 5 4s. We saw 3 3s, we saw 6 2s, and we saw 2 1s. 5 plus 3 plus 6 plus 2 is 16. N equals the number of observations. We had 16 observations. Right?
Yeah.
Clear on that? We okay now? You got it now? All right. All right. Any more questions about the homework? All right. Go away. Okay. Time for some math. Time for chapter 5. Time for an actual almost statistic. Anybody here ever heard of a z-score before? Jake? One? Anybody else? High school stats? All right. This is where we're going to take simple arithmetic and apply it to probability theory. Today we're going to do the simple arithmetic. Next class, we're going to throw the probability in there. Because I can tell you what a z-score is. A z-score is just a transformation of our numbers. That's all it is. Right? You can call it standardization if you want. I don't care what you call it. Just don't be scared. So we've looked at this curve before. This is the normal curve. This is our bell curve. It's our normal distribution. What's the area of the bell curve? Okay. Why is it always 1? Because it's a percentage. It's not inches or cubic feet or anything like that. It's always a maximum, a percentage of 1. Right? It represents area, the proportion of the area under the curve. Now, we have talked about this part before. The bottom is known as the x-axis. The one that goes up and down is known as the y-axis. There's actually a z-axis that, if this is x and this is y, z goes like this, which is really hard to do, and you really got to light a candle and have a couple of beers. Because it gets all cloudy, like it rotates and spins. There is also a z-axis. That's 3 dimensions. All right, we're going to stick with 2 flat dimensions. So on our z-axis, what we have here, for example, when we were talking about the empirical rule, we were measuring the area under the curve in terms of the standard deviations. So 68% of our observations are going to be within plus and minus 1 standard deviation. That 68%, 0.68, is the area under the curve. 95% of our values are going to be within 2 standard deviations from the mean. So again, we have the mean. That can be an actual number. We can then also have a separate x-axis, that is the standard deviations. If we wanted to, we could think about this in terms of percentages. The cumulative percentage, if we start at the lowest number at 0%, our halfway point should be 50%. Remember, it's a symmetrical curve, which would leave us with the other 50% on the other side of the curve. All I'm going to do today is introduce the concept of a z-score, which is, here we go, another transformation of the data like we have before. If we start with actual scores and then we go to standard deviations, then we can go to percentages, and now all we're doing is creating a nonsense number called z. Okay. Z, the way it's distributed is to fit the area under the curve. So we're going to start in the middle with a z-score of 0. So z on a normal curve, always, whenever you draw one, this is 0. It's set to have the 50th percentile. It's set to be the most frequent observed number. And as we go out in a positive and a negative direction, we're going to go out to about -4 to +4. Right? We get these, you might have noticed a little bit that the z-score and the empirical rule match up fairly well. That's not by accident. Right? So the midpoint for a z-score is 0. The empirical rule starts at 0 as the standard deviations from the mean in the center. When we go out, our z-score of 1 represents 1 standard deviation from the mean. A z-score of 2, 2 standard deviations from the mean. 3 and 3 and 4 and 4, etc. You got that? Okay. Why do we do this? Well, we want to figure out for all of the distributions that take the shape of a normal curve, is there a way that we can find out the area under the curve from that point? And that's what Z was created to do. So if I tell you that I have a z-score excuse me, one more time. If I tell you that I have a score of X, like Einstein's IQ, where would that fall in the range of all IQ values? Pretty far up there, right? Well, according to this picture I found on the internet, and of course everything on the web is true, let's say Einstein has an IQ of 160. Sure, why not? Where would that place him in the distribution of IQ scores? Well, I do know one thing. I do know that the average IQ score and how they built the test is based upon a 100. So if you've ever taken an IQ test and you've gotten above 100, you are above average. Now that doesn't mean that you are in the top 50%. It just means you are, again, air quotes, above the average. Whether or not the average IQ score is actually 100, we don't know. But we've been told that that's what it should be by the people who made the IQ test. So let's say you get a score of 160. You're way the hell out here. How different are you from the average person? Well, we can say that you are 60 points higher. But how many people in the world are like that as well? This is where we get into this. Well, it would be really nice to know the area of the curve used up between the mentally inadequate all the way up to the exceptionally gifted. How much of this area is before that point on the curve? How much of it? Any guesses? Okay, 0.9, a lot, but not all, right? I mean, you got to be really, really out here, right? Because this doesn't look like it's very big, right? This section here. Another way of thinking about this is if we start at 1 and we subtract this number here, that tells us how many people are technically above Einstein, right? To the other side of them. So that's why we created z-scores. We created z-scores so that we can compare a value of x with what is the expected distribution of that characteristic, like intelligence. Does that make sense to you? Anybody really freaked out right now? We all good? Okay. So all we're doing is converting our x that we're given to a value in terms of z. That's called the z-score. Okay. So here's an equation for you. Z, the score we're looking for, which is an actual z, it's not a z, we just call it z, is equal to x. X is the value of the observation. So in the previous example, what was x on my slide from the internet? No. What was x? No. Which was 160. All right, so if we're going to use the Einstein information, Einstein's IQ was 160. Subtract that from the mean. What is the mean IQ score? We think it's 100. We were told it's 100. Divided by the standard deviation. Crap. Because I didn't give you that in the previous slide, did I? Here's the thing. It changes with every data set. 9 times out of 10, when you're given a question on a test or a homework, you're given the standard deviation. Or if they want to be tricky, they give you the variance. Because the variance is what relative to the standard deviation? It's squared, right? So like I said, most times this is just given to you. Stupid internet didn't give me the standard deviation of IQ scores. Let's just Google one and see what Google says. Standard deviation of IQ scores. $15. According to Google talkie person. That doesn't have a name, does it? It's not like Cortana or Siri. Does the Google talking lady have a name? No. Google lady. She who Googles, Google says that the standard deviation of an IQ test is 15. So where is Einstein, his IQ on that z-score chart? Well, let's do the math. 160 minus 100 divided by is, okay, z of Einstein. Four. Way out here. It's so small that giving you the number actually doesn't fit on the chart. What chart are you talking about? Well, don't freak out. Keep eye contact with me. Don't do it. So what have I given you? The standard normal probability. Very good. Oh, I didn't leave it up on the web. Oh, well. Don't worry, I'll edit all this out. Okay. Here we go. Now, I can't write on the screen. It's a PDF, but what do we have here? On the, I guess, your left-hand side, you have a value of z. Okay. Let's start on the one with the positive numbers, 0.0 in the upper, there you go. That's your positive z-scores. So if we get a z-score of 0.00, we know intuitively, just by understanding where z comes from, that what is that point? It's the mean, right? It's the middle. It's the dead set middle of the curve. So when we look on our chart and we go 0.0 on the side and we go over to 0, so again, two figures after the decimal, 0.0 in the row, 0.0 in the column, we get 0.5000. Does that make sense?
I was just pointing out that you're holding that side of the screen.
Oh, dope. Thank you. This is one of those things that because it's symmetric, like in some textbooks, they don't even give you the negative side. They just give you the positive side. Thanks for pointing that out, Tom. Right? So a z-score of 0.0 and then 0 is 0.5. Now, what is 0.5? 0.5 is the shaded area under the curve. So half of the observations are to the, as we're looking at it, our left of the z-score. Does that make sense? Not really. One more time. We have a curve. All of the area under the curve adds up to 1 because it's a proportion, right? The area under the curve in terms of the proportion. The shaded area represents how many observations are under our value. So if we start with a z-score of 0, which when we created z-scores, we meant that to be the midpoint, or whatever the mean is for our distribution, that means that half of it is in the shaded area of the curve, which would mean that it would be this part of the curve. Okay?
So you're saying if you start at 0.0, that 0.5 represents that.
Yeah. Oh, bad curve. We know that when we established a z-score of 0, that this area under the curve so essentially what we've done is we've said you're an average person. Who wants to? Joey. Joey takes the IQ test. Fake Joey takes the IQ test. Joey's average IQ, Joey's personal score is 100. The average score is 100. Google lady tells me that the standard deviation is 15. Joey's z-score is 0 divided by 15, which is 0. I go take that z-score, I look it up in my table, and I know that 0.5% of the, or 0.5 of the population, or 50% of the population, has a IQ score less than Joey. Let's try to look up Einstein. Einstein's z-score was 4. The table doesn't even go that high. Right? The table goes up to 3.49 because you got 3.4 in the column and then not, or in the rows, the bottom row, and then the 9 digit on the column. So Einstein's way out here with his z-score of 4, which represents a IQ score of 160, right? What percentage is it? Well, the area under the curve for Einstein we know is greater than, and I can never remember which one it is. I always think you point at the littler one. So let's go with that. Is greater than 0.9998. So tenths, hundredths, thousandths, 10,000ths. So if you had 10,000 people surveyed, Einstein would be in the top 2 people. Does that make sense? That's how rare a z-score of 4 is. Okay. Let's do Jake. Jake takes the SAT test. Jake gets an 80. We know the average is 100. We know that standard deviation is 15. We do the math. Negative 20 divided by 15 equals 1.25. That's negative. So let me ask you, for a negative 1.25, how much area does that account for under our curve? So we look on the chart. We turn it over to the other side where the negative numbers are. Negative 1.50. Or sorry, 1.25 gives us an area of 0.1056. What's the area on this side of Jake's score? So how many people, what proportion of the people scored higher than Jake? Hmm? 89.5% of the people who took the IQ test scored higher than Jake. Again, Jake, not our Jake. So what would we say about Jake's intelligence? Enough with the microaggressions. We would say that Jake is educationally IQ challenged and needs additional resources so that he can reach his full potential. Not that you're dumber than, everybody almost. IQ tests are bullshit, by the way. We try to quantify intelligence, but you can't, right? I took an IQ test one time and received a score of 144. Do I look that smart? No. No. I do stupid stuff all the time.
The other thing is they measure it on babies too.
Exactly. Right? So in 2nd grade, Abby's going to be tested to see if she goes in the gifted and talented program. She's 7. In 2nd grade, she'll be 8. You know why she'll score higher than everybody else? Because she's the oldest kid in her class. She missed the school cutoff by 4 days. Right? So when she's a senior in high school, she'll be the one that goes out and buys everybody cigarettes. Because she'll be the first one to be 18 years old. And hopefully it's because she's 18 and not because she has facial hair like her dad did when he was 15 and was the one buying cigarettes for everybody. All right? So she will have an advantage. She will also be the tallest person in her class. She already is. So when it comes time for sports, she's going to be awesome as a senior because she'll be developmentally the same as a college freshman. So there is a reason for some of this stuff and why you can find disparities in things. But IQ tests are horrible. They really are. I am not 144 point smart. It just doesn't work that way. Okay. So this is a Z-score. All we're doing is comparing a number that we observe to the mean, right? And again, when I say the mean, I think the mean. Hopefully it's the population mean. It might be our sample mean. And we're accounting for the distance away from the median based upon the amount of spread in our data. Does that make sense? So that's why when we do statistics, we do baby steps. The first part is to understand measures of central tendency so that we can understand what a mean is. The second step is to understand variance or spread, because the variance is what changes the shape of that curve. And now that we have mean and variance, or standard deviation in this equation, we can start comparing individuals and their scores to the mean. Whether it's the mean of the data, so of our 2,306 people that rated Hillary Clinton, we can see where individuals would be relative to the mean. And again, all that depends upon the shape of the curve. So when your last homework talked about skewedness, we kind of want to know whether or not we're dealing with a normal curve or not. But again, for the most part, for reasons that I'll tell you probably next week, we just assume a normal curve. There's this thing called the central limit theorem, also known as the law of large numbers. We'll get to that. But all I want you to do now is to understand what a z-score is. It's a way of recalculating an individual observation relative to the mean and the variance. Does that make sense? Okay. Now, we can do a lot more with this concept of z-scores if we add in probability. So let's think about it this way. If I received 144, and I'm just going to round up to 145 for math's sake. My chart does have 3 on it. This area is equal to 0.9987. Still pretty small. It's basically 13 out of 10,000. If we add probability into this, we can then say, what is the probability of somebody scoring greater than a 3? Or less than a 3 in taking the test? Because probability theory, like a proportion, is also bounded between 1 and 0. Remember when we did probability with dice, right? Probability of rolling a certain number, 1 6 plus 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 1 6, you always top out at 100, right? You always top out at 1. We're talking about percentages or proportions. So because those two things are the same, we can put this on top of this. So area can not only represent proportions or percentages, but it's also going to represent probability.